to physics. Welcome to week 4, hardly. Let's see. Not a ton of sort of announcements at the beginning. Today we'll cover C7. Next class we'll cover chapter C8. We're at a point now where we're sort of stepping through one chapter last session. There will be lab sessions this Thursday at the usual times. We'll probably do more video analysis. I'll figure that out probably tonight. Let's see, homework help is over on that. I'll email this out also, but it's also over on that board. You can take a picture of it if you wanted. I think the homework this week will not be, likely for most folks, will not be as challenging as the homework for this week, but will not be, if this was week 2 and this was week 3, like this might be week 4, in between week 2 and 3. I think the homework for C6, which is already posted, I think, is nothing too crazy. There's some more interesting problems for C7, which I'll assign this afternoon. Again, nothing too crazy, but lots and lots of time to get help. Always feel free to reach out to us on email. If those times don't work, let us know. We'll figure something out. I can stick around for at least 10, maybe 15 minutes after class today if people have questions or want to check in on anything. All right. So today, we're going to talk more about potential energy. So we did potential energy last time, the formula mgz, and we're going to do more with different types of potential energies and potential energy formulas. So let's see. So some reminders. Energy is this quantity that, like momentum, is conserved. It stays the same. There's kinetic energy. Yes. What color do I want to use? So I've got kinetic energy. And that's a property of an object. So a moving object has some kinetic energy. You drop a ball off of a balcony, it gains speed and hence gains kinetic energy. This is potential energy, which is associated with an interaction. So we would say before you drop the ball off of the library balcony, it has some potential energy. What that really means is that the ball-earth system has some potential energy due to the gravitational interaction. And what we learned last time, and this is so this formula, which you got some practice working with, and you'll get practice working with in the homework for C6, is a lovely formula. It's only true near the surface of the Earth, however. And physics, being the most ambitious and true of sciences, seeks to make statements about the entire universe, not merely what happens on the surface of the Earth. And so what we'll talk about today is what's called the universal law of gravitation, which is what Newton came up with whenever Newton was doing Newton things, which was what, 1660? I don't know, a long, long time ago. So So what we'll do is we'll spend 5 or 10 minutes unpacking this equation, and then I'll do an example of this equation, and then you'll do an example of this equation. Okay. So what is this? This is the potential energy. Probably easier just to draw a picture. We've got two objects. So two objects. And it's already starting. My two supply is already dangerously low. So we've got two objects, and massive objects attract each other. Gravity is always an attractive force. And we could describe that as a potential energy, and the formula for that depends on the following variables. So it depends on the mass of one object and the mass of another object. Double the mass, you'll double the interaction, double the energy. And then it depends on the distance between the centers of mass of the two objects. So the farther apart they are, so if R gets bigger, this gets smaller. The energy is, the quantity of this gets smaller. G is a number, a constant of nature, known as the universal gravitational constant. This is true everywhere in the universe. And it happens to equal 6.67 times 10 to the minus 11 joule meters per kilogram squared. So this number is experimentally determined. I think it was determined, well, a number of different ways. If you know like how the moon orbits the Earth, you can use that to figure out what this has to be, and then you can figure out G. It was also, I think, measured directly in a lab in the 1700s, maybe by Cavendish. I don't know. The point is, this isn't something you can derive. This is just a fact about the world, like how big electrons are. All right. Let's see. Try to decide if I should draw. All right. Let me sketch this function. Because I'm guessing you're looking at this and thinking, this seems a little weird. Like this was kind of nice, and this looks a little strange. What is it? Let me draw a graph of this. So this is V of R. And notice there's that minus sign there. And so I'm going to see what happens as I change R. As R gets smaller and smaller, what happens to this expression? It gets bigger, yeah. And except there's a negative, so it gets bigger upside down. So it's going to look like this. And in this, V equals 0. So from Thursday's class, there's that business of having to set a reference position. When you're using this formula, the reference position is implied, assumed to be at infinity. So when the two objects are very, very far apart, their interaction potential is 0. That sort of makes sense. They're at opposite sides of numbers. And then the potential looks like this as R gets smaller. I think maybe the way that this graph makes sense to me is, suppose raise the lacrosse ball up, like I gave the lacrosse ball to some of you and you walked upstairs with it, you gave it potential energy, so you increase the separation. So when you increase the separation between two objects, the potential energy increases. Right? Because if I were to drop that object, the higher up I drop it from, the faster it hits the ground. So this is showing if I increase the distance between the two of them, the potential energy increases, which is what you would expect physically and what we saw physically last time. All right, let me do an example just to show you how to use this formula, and then we'll do an example, and in so doing, we'll compare this formula to this old formula. Okay, so today is going to be a day to work on your relationship with your calculator. If it's not perfectly strong, today will be a day to strengthen it. We're going to be doing, you can sort of see this coming. There are going to be some really big and some really small numbers. It's like these are going to be like planets and stuff. So I think on the other side of this page is the example that I want to do. Example 1. So imagine, I guess I will start over here. So you're on, is it the moon? Yes, you're on the moon, and maybe you just harvested some cheese from the moon. If the moon is indeed made of cheese. And let's see, you are in a spaceship 50 kilometers above the moon's surface, and you decide to drop the cheese from the spaceship onto the moon. And you wonder how fast the cheese will hit the surface of the moon. Like, would it be fast enough to get hot and melt it? Would the cheese explode? Let's see. Okay. So there's the moon. And this is going to be 8 kilometers. And so R in this formula is the distance between the centers of mass of the two objects. Two objects here are the moon and cheese. So that is a brick of cheese. You can tell because it's yellow. Cheese is always yellow. So initially, like when the cheese is dropped, what would we want to use for R? Yeah.
Is it 50 plus the radius of the moon?
Yeah, so it's going to be 50 kilometers plus moon radius, 70. And then when it lands, it's not at 0. Yes, it's on the surface of the Earth, but it's, surface of the moon, but it's 1 moon's radius from the center of the moon. Which is 1740 kilometers. So we're going to need to convert those into meters. So this is going to be 1.79 times 10 to the 6 meters. So millions of meters. got the mass of the G's, and we've got the mass of the moon, which is a very large number, 7.4 times 10 to the 22. All right. So we're going to use conservation of energy like we did before. It's just we're going to be using this formula instead of mgz. So, conservation of energy. I'll do 1 and 2. So initially we have kinetic and potential. This is right before the T's is dropped. And then afterwards we have kinetic plus potential. So, let's see. Oh, and I should mention the initial speed of the T's is 0, yeah. And the T's when it hits the ground, the speed of the T's when it hits the surface of the moon is what we're trying to figure out. Okay, so minus G mcm m over R1 plus 1/2 m v1 squared equals minus G cheese moon R2 plus 1/2 m v2 squared. What mass should be here? Cheese, yeah, it's the cheese mass. So there was a similar student, Casey Ackland, who graduated, oh my gosh, 5 or 6 years now. Steve on the island worked in the lab for a little bit. And he took a lot of classes from me, and he took TA a whole bunch of classes, and so he did a lot of the let's go around the room and everybody share a block type of exercises. And he would always want to do say your favorite cheese. And then it became this ongoing joke that everybody would outvote Casey doing favorite cheese. Anyway, so anytime cheese comes up in a class, I always think Casey would be appreciative.
Casey means cheese in German.
Oh, yeah, Casey Ackland, yeah. I don't know. I think he just liked cheese or thought it was funny. But yes.
Does that say H equals 50 kilometers up there?
Does that say what, sorry?
H equals 50 kilometers up, like by the drawing.
Oh yeah. So that I was thinking. Yeah. So H is the height above the surface. Yeah. I wasn't quite sure what to call it. Yeah. But the main thing is that it's not R. So R has to be measured from the center. Okay, so now, let's see. So, turns out the cheese mass doesn't matter. And we're going to solve this for V2. And this, V1 is 0, so that's going to make this term 0. So I'm going to all right. So a little bit of algebra. So I want to get V2 by itself. So the first thing I'm going to do is move this term over to the left by adding blah to both sides. So I'm going to do that. See what happens. All right. So adding this to both sides, I'm going to get plus G moon over R2 minus G moon to do two things. I want to multiply by 2, and I want to factor out a GM here. Maybe I should do it in 2 steps or 1 step? I'm going to do it in 2 steps. You can do it in 1 step if you want. So first I'm going to factor. I'm going to say, hey, there's a big GM in both of these terms. So I claim I could write this like this.
It's multiplied by 2.
And I guess you don't have to do that, but it'll save you a bunch of calculator work. And then I want to get this 2 over to the left, so I just multiply both sides by 2, G, M, 1 over R squared. Nope, yes. 1. And so I'll need to take this, to get the 2, I'll need to take the square root of both sides. But probably let's start plugging in some numbers first. And then we'll need to square root. And so we'll see how the units work out. And so this is the part where you'll need to make sure you're in the right relation to your calculator. Because we'll have to do a bunch of scientific notation. I mean, you can't, if you have questions about how to do scientific notation on your calculator, let Annika or Elsie or I know, and we'll be happy to look over your shoulder. Another option is to type in the Wolfram Alpha, and I forgot to bring my laptop today. But that can be helpful because it shows you what you just typed in, so it becomes much less difficult to catch entry errors. Anyway, if you're having any struggles with this, that's totally normal. Just let us know. All right, so let's see. So let's plug in numbers. 2, C is 6.67 minus 11 joule meters per kilogram squared. The mass of 7.4. These are meters.
Isn't it supposed to be R2 minus R1?
Yeah, so 1.74 would go first.
Oh, okay. Yep. Unit 6. Okay, thanks. And so what I feel good about that change, because it's correct, but I can also see it sort of has to be that way. Something minus something is equaling b squared. So it's going to be a rough day if this is negative. So this number is smaller than that number. That means that this number is going to be bigger than that number, and I'm going to get a positive number, so that the cheese will not land with an imaginary velocity. Okay. Let me see. I will confess that I did this all in one big step, which maybe I should have done. 1.74 6. So I got this number in 5.74. anybody getting similar things? Is anybody getting things at all?
I did it all in one big step.
Okay, okay, that's, what was at the end of your big step?
398.1.
Oh, after square rooting, yeah. 398. So you should end up 1.8 times 10 to the 5. Or b squared, interesting, b 398, is that what you got? Yeah. Let's see, let's ponder units to see how the units work out.
Would be 2 squared?
This is b2 squared, yeah, thank you.
Yeah, right, velocity.
No, now I'm in trouble. My supply of twos. Oh, and this should be, these are meters on the bottom. Right, because there are meters downstairs. So what's going to happen is, let's just take care of the units here. Meters, 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 and then those are gone. A joule, remember what a joule is? Kilogram? Meter squared per second squared, that's a joule divided by a kilogram, and this is just delightful, the kilograms cancel. Meter squared per second squared, which is exactly what velocity should be. Square root meters squared, square root second squared, you get this. Okay. So I'm going to propose that we now do another problem. And we're actually going to do this problem two ways. Using our new potential energy formula and then using our old potential energy formula. So give problem 1A a try. And then we'll also do problem 1B. And we'll talk through things. And we can stop. Okay, so we did the problem two different ways, and we got similar but not identical answers. Let's see. Should we have expected them to be identical?
You should edit it.
Let's see. So, let's see. There was a clear hope there. I'm sensing a hope, a desire that they be identical. So this formula, mgz, only works near the surface of the Earth. Whereas the other formula, I've claimed, is universal. It works everywhere. And so the issue then is 400 kilometers above the Earth close to the surface of the Earth? I mean, it's sort of close because the radius is 6,400. But it's also, like this is also not particularly close to the Earth. So this is sort of be like right on the edge of if you could use those, if you could use the simpler mgz formula. Here's another way to think about this. The mgz formula assumes that the gravitational interaction is constant. Right, that little g, that sort of force of gravity, acceleration due to gravity, that it's the same even when you go up high in the air. But when you're higher in the air, the force of gravity decreases. You're farther away from the Earth. So this approach accounts for that. That the interaction strength weakens as you get farther away. So that's why the speed done this way is a little bit less. Because you're not accelerating at the full 9.8 the entire journey down. Okay, let me attempt to tell that story again using a graph, and then we will shift to talking about springs. So, okay, so this formula, if I wanted to plot V as a function of Z, what does that function look like? Is it Z squared?
V increases and C decreases.
It's going to increase as Z increase, and it's going to be a straight line. Because it's not like Z squared or Z cubed. You go up twice, like if I told you to walk to the roof of the library with the lacrosse ball, it would be much more exciting. I don't know how you get on a roof. Probably dangerous. I mean, it's definitely dangerous. If you for every meter you go up higher, your potential energy goes up by a certain amount, and it just keeps increasing. So it's a linear, straight line function. This would be like a number times Z. Then this is what that function looks like. And it's definitely not a straight line. It's a curve. However, if you're close, so this might be, maybe that's the radius of the curve. So I claim if you're close to the radius of the Earth, this is going to look like a line. And you can see that geometrically as follows. And you can try this if you have written this on your piece of paper. Go up really close. And it will look like a straight line. And that's the main idea. It's like, that's what calculus is, or calculus 1 is. It's saying, hey, we can, the curves look like lines when you get close to them. So you could use calculus to say that when you're near the radius of the Earth, this, the slope of this line turns out to be that. They have the same slopes. So I will write an optional problem. It actually doesn't require calculus. You can do it just with algebra, but it's a bunch of algebra I've done. I feel like I'm already dangerously close to maxing out algebra today. I'm also not done with algebra. To show that these two formulas, that this, near the surface of the Earth, mathematically reduces to that. And again, if you've taken calculus, or sometimes maybe in pre-calc, you're used to that idea that you can approximate curves with lines. And if you haven't taken calculus, the idea that you have something curvy, and you zoom in and it looks straight. That's all it is. Okay. So I would like to shift gears and talk about another type of potential energy. And I'm going to propose we take how about like a 4-minute break? So you can put your head on the table, you can go outside, get some air, drink some water, stretch your legs. But let's come back in 4 minutes. I'll erase the board, and then we'll spend the remaining time, whatever it is, 25 minutes, talking about springs. All right, welcome back. So the last topic for today is springs, which will involve less crazy numbers and somewhat less algebra than what we just worked through. So let me start by talking about springs. Then we'll do an example, and then I'll say a little bit why springs are actually important. Okay, so spring. So here's my rendition of a spring. So you have a spring, like a coil of metal, and it has some relaxed length. When it's just minding its own business, being a spring, it has some, like this is what the spring does. And then you might like put a marble on top of it, and then push that spring down. And so then you would compress the spring. And then if you suddenly released it, the spring would spring. That's what springs do. The spring would spring back, and it might launch this marble upward into the sky. Does that picture make sense? Okay. So you've got a relaxed spring. You press it in. And so there's clearly some potential energy there. Because if I let go, it can give kinetic energy or kinetic energy to this marble. So what is the formula for that? It turns out that the okay, so it turns out to be 1/2 ks x squared. So x in this is the amount by which you compress the spring in. You could also take a spring and stretch it outward too. Same idea. And then ks, so it's called spring constant. And so the spring constant, it's called a constant, but it's not constant, in the sense that it's different for different springs. Some springs are stiffer than others. Some springs are very easy to push in, some springs would be a lot harder to push in. And accordingly, they would launch this marble at different speeds. So let's do an example, and then decide if you want to do an example or not. I suspect you might opt out. That's fine. But I wanted to spend a couple minutes at the end to talk about why springs are relevant more broadly to physics. So let's look at example 2, which you'll find underneath example 1 on the other side of the page. Ks for the spring. And so x is not the length of the spring, nor is it the length of the spring after it's been compressed. It's the amount by which you have compressed it. So x is 3 centimeters and 1 meter, 100 centimeters, so that's 0. So what I want to do, we're going to conserve energy, and we're going to conserve energy in the following two moments. Moment one will be when it's compressed inward, and moment two will be right after it's done uncompressing itself. So I might just draw that. X1 is so scenario one, the spring is compressed, the marble here. Scenario two, the spring has sprung and the marble has just begun its upward journey. Yeah,
And x2 is 0 because the spring is back to what it's supposed to be.
exactly. Yeah. Yep. And oh, let's see, the mass of the marble, 18 grams? What is it?
12.
12, okay. 12 grams and 1 kilogram. So that's 0.012 kilograms. So, we'll conserve energy. Well, we were on a break, I replenished my supply of tubes. So now I feel much less nervous about tubes. Let's see. Is there something you notice not happening that has always happened before? The M's don't cancel yet. M's don't cancel. And that's because like this is a spring, like a fact about a spring. How stiff a spring is doesn't depend on the mass of what you put on top of it. All right, we do have some zeros to work with, so that's good news. The initial V is 0. And the second, that's 0. So that's going to make this algebra pretty nice. So this is the spring after it's, right, because the spring is unsprung, it's back to its equilibrium position. And here, because we want, it's at rest before it gets launched. And let's see, what are we solving for? We're solving for V2. So let's do that. So first I'll just write this over 1/2 AS x1 squared is 1/2 mv2 squared. We do have halves canceling now. So I want to get v2 by itself. I'll divide both sides by m. That's v2 squared. And so now we can plug in some numbers. So let's do that. KS 450 joules per meter squared. X1 is 0.03 meters squared. M is 1.312 kilograms. And I got 1.83. Oh, I think I made a mistake when I did
Is
this.
that 5.8?
That sounds better. So just to look at the units, meter squared, joules over kilograms. That's familiar, that's what we had before. A joule is a kilogram meter squared per second squared. The kilograms cancel meter squared per second squared, which is a great unit for velocity squared. Turns into meters per second. Okay. So now we know how to work with springs, and now we know how to apply gravity anywhere in the universe. But those are sort of, how do I say this? Gravity anywhere in the universe, that's like pretty far-reaching. Springs are cool, you can shoot marbles with them. So it sort of seems weird, like, who cares about springs? Well, it turns out that this formula applies to things that aren't like actually springs, but are spring-like. So let me end by just spending a few minutes talking about that, and that'll be a preview of what will, I think, be coming soon, like in a week or so. So I will plot this potential energy as a function of x. X is spring compression. What is this going to look like? Ernesto was doing this. This is going to be a parabola. Because it's x squared. So anything, let's see. So a spring is going to look like a parabola, but it works in the other direction. Like any parabola-like potential energy function is going to have a potential energy that's quadratic, that looks like a spring. So one example would be intermolecular bonding forces. So oh, and I should mention, again, this is a preview of what's to come. The equilibrium position is going to be the lowest potential energy. That's what the spring wants to be as Elder. We all want to be at our lowest potential energy. So this might be the potential energy function for a molecular bond. Sometimes called a van der Waals force. Maybe a chemistry teacher has mentioned that word. Awesome. Does Ruben talk about van der Waals bonds? Does he draw these pictures?
Not really.
All right. So, deep in his soul, these pictures are what he is thinking. So this basically says two molecules, they really don't want to get super close to each other. But there's this region in between where they're bonded together. And so there's going to have to be some sort of a minimum for that sort of potential energy bonding thing. And that's going to look like a parabola. And so you can describe, for example, molecular vibrations as if they were as if the molecules are connected by a spring. And so that's not merely like I mean, I guess it is and it isn't a metaphor. It is a metaphor because there are not literally springs that connect molecules. I don't know much chemistry, but I know that. But mathematically, they behave as if they were. So you can do conservation of energy sorts of problems, figure out frequency of oscillation, even if it's not actually a spring. So anything that that has a potential energy function with this sort of equilibrium, which includes almost all molecular bonds, acts spring-like. So springs are not, it's not quite as grand as, hey, here's a law of physics that's true everywhere in the universe, but it turns out to be this turns out to be a really, really useful formula and result. And we'll do a little bit with this, I think in C10, maybe C11. So that is plenty for today. I think I'd stick around if people have questions. I will post the homework later this afternoon, the rest of the homework later this afternoon if you want